are able to take off, thanks to the thrust that is higher than the drag, what will happen? You see, the thrust minus drag is increasing. And so, what will happen? You will have the largest thrust minus drag here. And as above 36,000 feet, TA is not anymore influencing the problem, you will, from there, follow the parallel evolution with this one. And from here, the thrust minus drag is constant. But you have the thrust minus drag that is maximum where around 11 kilometers altitude. So, is it a bad point that the thrust is decreasing with the altitude? No, it's a good point, because when you compare it to the drag, the optimal flight altitude from a thrust point of view is around 11 kilometers altitude. So it's very clear in the explanations that we have given. Now, there is another one that we need to consider. This is this one. This one is a bit more difficult to tackle. Why? Because I have written the thrust as rho A VA AA multiplied by V jet minus VA. Okay? VA is, let's say, increasing, so this term has a negative impact with the minus VA. Okay? And a lot of you would say, yes, but I have a very positive effect here. VA is increasing. So m dot, because this is equal to m dot, will increase. No, no, no. It's not true. Why? Because we don't know how this parameter is changing. I remind you that AA is not a fixed area. And if this area is changing, we don't know how it's changing. We don't know if it's changing, and so we don't know how it's changing. And so you cannot say that m dot is increasing. In order to understand what's happening with m dot, you need absolutely to write this term as a rho1 v1 a1, for example. Why this one? Because you need to have a fixed area. You need to have a fixed area, and a1 is a fixed area. And I don't have the time to discuss that, but if you take an isentropic flow, I know that the flow is not really isentropic between the section A and the section 1, but it's not far of being isentropic, because you have only the ram recovery, and I said to you, we will explain that later on, the ram recovery in a subsonic transport aircraft, in cruise this is maybe 99.8%, so very high value, so it's almost isentropic. And you can see that when you are decreasing the speed from VA to V1, and this is what's happening in the intake, we reduce the speed from VA, that is, I don't know, 250 meters per second, down to V1, 150 meters per second, you can have a look with the isentropic laws, you will see that rho1 V1 will increase. This is a rationale that is scientifically correct. And indeed, you will have m dot that is increasing. Because rho1 V1 will increase from a certain value of VA. When VA is small, it's not increasing, it's more constant. And then at a certain moment, when you have what is called dynamic compression, so when VA is becoming equal to 150 meters per second, roughly, you need to decrease the VA down to V1. You will have what is called dynamic compression, and ρ1, V1 will increase, and M dot, will also increase. Another factor that will play a role, this is V-jet. The V-jet will be also influenced by the value of VA. It can be in different ways. For example, when you increase VA, the V1 that you have here will at a certain moment increase, and at another time this is more ρ1 that will increase. In fact, this is P1 mainly that is increasing. And globally speaking, this is PT1 that is increasing. And so what can you do at a certain moment when you are flying at high speed? What will you do if you want to fix PT2? You say PT2 has reached a certain maximum value. If PT1 is increasing, you will say, I will reduce my pressure ratio. And if I reduce my pressure ratio, I take less power out of my turbine. So I have my turbine here, and my turbine will have a lower expansion ratio, and the PT4 and the TT4 will increase. And so I have more energy behind my turbine, and I will, thanks to that, increase V-jet. And so what's happening when you look at, I will draw that here, when you look at the evolution of the thrust with VA, so I'm starting from takeoff. I will first have a decrease due to the minus VA, and then with the slow increase of VA, this dynamic compression is taking place, and even later on, this effect that you have on V-jet, and so you will start compensating this decrease, and you will have something like this. And so maybe at, don't know, 0.7 or something like this, you have compensated this value, and at 0.8 you have increased the value, and when you are at, let's say, 1.5, let's say, you will have a thrust that is higher than at takeoff thanks to VA, by the increase you have in m dot. Very often the people are saying that the turbojet is what is called a constant thrust engine, because compared to the cycles that we will see later on, you see that the thrust is roughly constant. It's in fact decreasing, increasing, but globally speaking, the thrust is not changing a lot in the subsonic flight range. Okay? What time is it? So I will conclude with the final evolution. The final evolution, which is the one on PLA. Okay? The one on PLA, I can explain it here. So, PLA, as I said, this is meaning m.f. This is the gas pedal. This is the gas handle. This is the throttle. You push in the throttle, more fuel, more fuel, more fuel arriving in the system. And if you have more fuel, you will have higher TIT. We know that higher TIT, this is very positive. If you have a higher TIT, we will explain that in the details later on. You will have a higher PIT, the power available on the shaft of the turbine. It will lead to an increase of the rotational speed. If we have an increase of the rotational speed, if you take the compressor map that we will explain later on, normally you have seen that already in some other classes, you will increase m dot, etc., etc. And so we see that we have an increase of the TIT, positive effect, an increase of m dot, positive effect, and also you will have a better value of the isentropic efficiency of the compressor, a better value of the isentropic efficiency of the turbine, a better value because the pressure is higher of the combustion chamber. All parameters related to efficiencies are getting better. And that's why, if you look at the thrust, which is equal to, if you look at the thrust, that is equal to m dot V jet minus VA. VA is a constant, because we change one parameter at a time. So when you discuss the change of the PLA, the altitude is constant, PA is constant, VA is constant. We change just the power lever angle. And what will we have? M dot will increase. And due to the higher TIT, V-jet will increase. Due to that, V-jet will increase. And so what will happen if you take the thrust in function of the rotational speed, because we express that in function of the rotational speed, between so 60% to 100%. Why do I take 60%? Because this is the minimum rating. We will discuss that later on. Also, what will you have? You will have a curve that is like this. A huge increase of the thrust with the rotational speed. And this is extremely important to mention. Why is it very important to mention? This is because you will work with an engine that is very, very much changing the performance for a small change of the rotational speed. And the 100% is there, but we will not work with this engine very often at 100%, only at takeoff, because we are too much increasing, for example, the centrifugal stresses in the blades, and we will go and work in this small range of rotational speed. Let's say between 90 and 80%. And what will we do? We will decrease the rotational speed during the flight. So we take off, high rotational speed, high PLA, high thrust, up to the beginning of the cruise. When you arrive at the beginning of the cruise,